All right, in this video, we're going to talk about average rate of change. And so recall that in the last video, or in the previous section, we learned that the slope is a rate of change, right? It's your rise over your run, you're changing your y over your change in x. And when you divide two things, and these are two changes, we get a rate. And so that's why we call it a rate of change. And it gives the rate in which the function is increasing or decreasing or what have you. And we interpret the slope as the increase or decrease in your output or your y for 1 unit increase in x. And so we're going to look at two examples, and we did that for linear functions, and now we're going to try to apply this to other types of functions, at least the concept of rate of change. And so we're going to use the graphs to find the rate of change of each of the functions graphed below. And so here to the left, we have a basic linear function, and so let's try to find the rate of change of that function. Remember, your rate of change, I'm going to abbreviate that with ROC, equals your slope because this is linear. All right, this one, nonlinear, right? And so basically what we do is we try to calculate rise over run. All right, one of the things that we could do is we could try to just select 2 points and do your rise over your run. So I just arbitrarily pick these 2 points. In order for me to get to from this point to that point, I have to go up 1, 2 units, so that's +2, and I go to the right 1 unit, so that's +1. All right, and so my slope here is m equals, well, my rise was 2, my run was 1, so I get 2 over 1, which is 2. And as you probably are aware, this was that same function that we looked at in that table from last class, right? So that is for our linear function. Our slope is our rate of change is our slope, all right? Now we got to think about the rate of change for this nonlinear function. If you notice here, this is a parabola, right? And by the way, these graphs should have arrows to denote that these continue forever. Sorry about that. However, this is a nonlinear function. If I want to try to find my rate of change, it's going to depend on where I'm at on the function. For instance, we already knew that we have 3 cases of graphs when we are dealing with linear functions. Our function can increase, that means our rate of change or our slope is positive. It can decrease or fall from left to right, that means our rate of change will be negative. Or it can be constant, meaning our rate of change is 0, or our slope would be 0. Well, depending on where we are on this function, if we want to think about the behavior of the function at least, is different depending on where we're at, right? For values on this portion of my function, our function is decreasing from left to right, it's falling, right? And it's falling pretty quickly here compared to falling over here. It's still decreasing, but it's not as steep in this area. The same thing happens on this side of my function. My function is increasing over here slightly, but it's steeply increasing as I continue to go up to positive infinity, right? And so here, rate of change, and I'm going to actually use the word here, for a nonlinear function, the rate of change is not constant. It's dependent on different values of the domain. And remember, we use that word domain to see is to be your set of all your inputs where your function is defined. So in this case, your x values. So depending on what x values I want to look at, I may get a different rate of change compared to x values in a different location, all right? And so that's why we have what we call average rate of change, because I can't get an estimate of rate of change using the same thing as what I did with linear function. All right, here, rate of change is constant. And so no matter what 2 points I pick, what x values I pick for coordinates, as long as I do this correctly, I'm going to get my correct slope, right? So here, I go up 1, I go to the right 1/2, so 1 divided by 1/2, that's the same thing as 2, right? Multiply by the reciprocal, you get 2, right? So no matter what 2 points you pick, you're always going to get that slope. Here, if I were to pick 2 points, for instance, here, I go down 1 and a half, right, a half, get these 2 points here, I go right a half and up 1, right? I'm getting two totally different estimates of rate of change, right? And that is why we have to look at what we call average rate of change. Okay, so the average rate of change of y equals f of x between x equals a and x equals b, right? We have to tell you on what interval for which x values to focus on, right? This average rate of change is basically going to be the slope, the same thing as your slope formula. I don't want to use the same variable as slope, and so what I'm going to do is I'm going to use an abbreviation AROC for average rate of change, all right? So the average rate of change is going to equal a rise over a run and then everything that you get from a slope or from x equals a to x equals b. I'm going to go back to this picture. Let's say that I selected, okay, I know this is a 1, but I'm going to call this a and I'm going to call this value here b, all right? Then I find the point with that x coordinate, I find the point with this x coordinate here. And so if I wanted to write this as an ordered pair, I'm going to write this point as an x coordinate of b. It's a little off, I'm sorry. B, and then since I don't know my function, I can say that this is f of b, and I'm going to call this point right here a, and this has a y coordinate, which is f of a, all right? And so what I do here, in order for me to get the average rate of change, I basically find the slope of the line, the straight line that connects those 2 points, all right? And so that is our average rate of change. Now, we already know our slope formula, right? Your slope is your rise over run. It's your change in your y coordinates. And so my y coordinates have this change here. This y coordinate to this point is f of b. And I subtract the y coordinates to this point here, which is f of a. And then my change in x is the difference, this distance here, which is b minus a. So that is a b minus a. I'm sorry, this graph is getting a little messy. And so I have my change in y, and I'm assuming that f of b is larger here, okay? Then I have my change in x, which is b minus a. And so it's the slope of that line. So it's going to be f of b minus f of a all over b minus a. This is the formula that we use. Note here, I could have called this x sub 1. I could have called the b x sub 2. Then I have f of x sub 1, and I would have here f of x sub 2, which we could call that y2 and y1. And if I did that, it will be the exact same formula as my slope, y2 minus y1 all over x2 minus x1. All right, so it's basically the same thing as a slope. You can remember this formula, or you can just remember the formula that you have for your slope. Another thing that I want to tell you is that this line that passes through these 2 points on the interval from A to B, if we go back to A and B, this line that passes through this curve at those 2 points is called a secant line. And basically, a secant line is a line that intersects a curve at 2 distinct points on an interval. All right, let's apply this to calculate the average rate of change of a function. Notice here, this is not a linear function. One thing about linear functions is that they are polynomials and the highest exponent is 1. This has an exponent of 2, and so that makes it nonlinear. All right, average rate of change, we have our formula there. We're going to have, this is our A and that's our B. So we have f of 3 minus f of 1 all over 3 minus 1. Well, we got to figure out what f of 3 and f of 1 are, right? So let's do some scratch work here. F of 3 means go to that function and plug in 3 for x. F of 1, go to that function and plug in 1 for x. That'd be 17, and that would be a 1. And so our average rate of change, which is the same thing as your slope of your secant line, remember that? 17 minus 1 over 2, which is 16 over 2, which is 8. All right? So remember, this equals a slope of your secant line. Since it's a slope, we interpret it very similarly to slopes, and we can get units very similarly to units of slopes. Let's look at another example. The table below gives the bicycle production for different years. All right, so we have years from 1950 to 2000, and we have the number of bicycles, the production level in millions from 1950 to 2001. It says find the change in bicycle population from 1950 to 2000. This is just a regular change. Change means subtract or difference. So if I wanted to know the change, and this is in your output, then I take the output for the year 2000 and subtract the output for 1950. And so since that's 101 and since that's 11, I get 90, and we want our units. These are changing Y values always, and so it's going to be 90 million bicycles. All right. Part B says find the average rate of change in the bicycle population from 1950 to 2000. We're going to give units and interpret our answer. Now we're going to do average rate of change. Well, that's F of 2000, F of B minus F of A. You're changing your output all over 2000 minus 1950. Now, F of 2000 is that 101. F of 1950 is 11. That's 90 over 50, which I believe is 1.4. It might be 1.8. Okay, and so I got 1.8. I just want to, your math teacher doesn't like doing math in his head, so he's going to get his calculator. Yeah, it's 1.8. All right, and my units here, notice this is a slope, right? It's going to be your change in your output. My output is in the numerator, right? It's millions of bicycles. I hope you can see that. I might be cutting off the screen. Okay, I'm pushing it very close. And that is divided by your years. So I'll say million bicycles per year. So we have 1.8 million bicycles per year. Now, this is a nonlinear function, right? So it's a curve, right? And so this is basically saying what we've just found for 1950, the year 2000, what we just found there, if we think about a picture, is this right here. So this may be the actual data on this curve right here, but what we found was an average rate of change. So we can't interpret it exactly the way that we interpreted our slope. So what we're going to do here is we're going to think about how we would normally interpret our slope and then adjust it ever so slightly. And so what we're going to have to be sure of is to include these things here, right? I'm going to say between 1950 and 2000, right? A slope gives you your increase or decrease in your output for 1 unit increase in your input, right? So my output is the bicycle. All right, I'm just going to say bicycle production. What we did was that's a positive value, so I'm going to say increased by, I'm going to say on average, 1.8 million bicycles per year. All right, an alternative way to say this is each year between 1950 and 2000, bicycle production increased on average, I'm using that on average because we have an average rate of change, 1.8 million BI per year. All right, that's an alternative way of saying that, but there we go. And I messed that up. I hope you saw what I had there because I cannot get it back. All right, I hope you got that down there. Sorry about that. So it's basically the same thing. It's the same. We're basically saying the exact same thing. I just wrote it slightly different. All right, it's basically the same thing. All right, that's average rate of change. Know that formula, know the connection, know how to give units and interpret things in the context of the problem, and you should be good to go. All right, see an average rate of change graphically. All right, question one, when a function is increasing, what is the sign of rate of change? All right, rate of change is usually at a specific point. This is a nonlinear function here. And so what I'm going to do is I'm going to notate when the function is increasing. All right, this graph has no endpoints. And so on this interval here, my graph is going up, right? So it's increasing on that interval. And over here on this interval, it is also increasing, right? When we increase, if we were to do a slope, our average rate of change or our rate of change, we would go up and to the right to get to the next point, right? Rise over run slope. That means your rate of change is positive. All right. Now on this part of my graph, my function is decreasing or falling from left to right. If I were to try to do a slope, I have to go down and then to the right. When you go down from one, when you're doing rise over run and you ever go down, that's a negative, and right is always a positive. A negative divided by a positive is a negative. All right. So we have that, right? That's same thing happens with average rate of change, right? You can kind of look at your average rate of change of 2 points on that interval. Bam, it's the same thing, right? So we can talk about functions that are nonlinear, increasing and decreasing, but again, it changes depending on the location that you're looking at specific to certain areas on your graph. All right, there are two other words that we want to look at, right? We want to know when the rate of change is increasing and when the rate of change is decreasing, right? For instance, when I look at this function here, for these values of x, my function is increasing really quickly, right? I'm steep here. The steeper the slope, the quicker I'm increasing, the more I'm increasing. But as I continue to get here, my function actually is going to start leveling off, on this side over here. So if I think about a slope is going to be much less steeper over here compared to a slope over here, right? So on this interval, it looks like, okay, well, I have a steep slope. It gets a little less steep here. It gets a little less steep here. It's less steep there. It's even less steep there, right? It's not, it's horizontal there. And notice it starts to get negative, right? So I'm going from some really big positive slopes to a zero slope till I get to negative slopes that start to get steeper. But after a while, those negative slopes that are steep get less steep, get constant, and then they get positive and get more steep, right? So what's happening here is that we have what we call concavity. Your graph is bending upward or downward, right? On this interval here, up until we get to somewhere in this area over here, right? We'll talk about how to find those specific points later. Our graph is concave down, all the way from here to here, somewhere in that area. But if I go and I look over here, my function is opening upward, right? So now it's concave up. And so if I think about what's happening on the intervals where my function is concave down, what my graph is doing, my rate of change is doing, is it's going from a really big positive number to a smaller positive number because the slope is less steep, to zero because the slope becomes zero, to some negative numbers. Well, when I come from positive numbers to zero to negative numbers, I'm decreasing. And since that represents slope or rate of change, when or this is concave down. When your function is concave down, your rate of change is decreasing. And the opposite happens when it's concave up. Your graph opens upward on this interval here. I'm starting with negative slopes, negative rate of change. Negative numbers become zero, then they become positive numbers. And they're steeper positive numbers. And so since my slopes are changing by those values, my rate of change is increasing. Okay, and so that is that. Last but not least, we're going to look at this example here, example 4. We're going to do A and B, and I'll have you do C and D yourself. It says, for which pairs of consecutive points on the graph is the function increasing and concave up, right? So what I'm going to do is look at where my function is concave up, right? I'm going to color it in, so to speak. It's concave down from A all the way until we get over here. And I know from C all the way until we get to like E is concave up. And notice it's concave down until it looks like we get to G, and then I know from G on out it's concave up, right? So I got the concave up part. Now I got to look at where my function is increasing. Well, it's increasing Not from C to D, it's going down from C, but from D to E, it's increasing. So I know from D to E, and also from H to I. Concave up and decreasing, well, the green interval was where it's concave up and orange was where it was increasing. Notice here, from C to D is decreasing and concave up, and G to H is decreasing and concave up. All right, that's all for now, folks. Catch you next time.